And this is so that you can start working on your second assignment right the minute you leave this class. Right? Because I know you've already finished the first one, and you're hungering for the next one. Right? Or, this time the guys at Microsoft laughed so loud that I even heard. And the worst is yet to come. No, just kidding. The deadline is on Friday, but the next class is on Tuesday, right? So that you can start working on it this weekend, and time is precious. At this point, you actually know everything that you need to know in order to do the Netflix prize. Okay? So let's look at collaborative filtering first, right, as an application of instance-based learning. And then as time allows, we will go back to many of the other issues and extensions and possibly continue next week. Okay? But the basic collaborative filtering idea is actually amazingly simple. So
how well does the weighted mean perform as opposed to the regular k-number?
They often do a lot better. And in particular, the reason we covered that before going on to collaborative filtering is that for collaborative filtering, it's absolutely essential. So nobody does collaborative filtering with unweighted k-nearest neighbor. Okay? And we will see why. Right? So this is a very interesting, it's both an incredibly important application in its own right and a very nice illustration of the issues that arise in doing instance-based learning. Okay? So collaborative filtering, also known as recommender systems. Right? Recommender systems are systems that recommend things to you. Amazon has a recommender system. Netflix has a recommender system. Every e-commerce merchant worth its salt has a recommender system. You can even think of what Facebook does as having a recommender system for updates, and Twitter as having a recommender system for tweets and so on and so forth. Right? And it could be for shoes, it could be for who knows what. Okay? 33% of Amazon's business comes from its recommender system. This is how important this stuff is. $1 in $3 that Amazon makes is because the recommender system is there. And for Netflix, it's 3/4. 75% of the movies that Netflix rents were suggested by the recommender system. No wonder, it's so important to them, right? And they proposed the Netflix price when the in-house data science team ran out of things to do. They were like, we can't think of how to improve the accuracy of the recommendations anymore. Let's just give it out to everybody. They're not going to be, and the goal was to beat them by 10%. Okay, and they were like, there's no way, nobody's going to do that. And then, of course, they did, and more besides. Right?
I also heard, just anecdotally, that Netflix, House of Cards, and other movies, original content is completely based on what people like as well. They came up with a plot made by these recommender systems.
And that's why Amazon and Netflix have such a high rate of success, is that they actually design their movies.
Exactly,
right?
Based on that.
It doesn't, the system, now it's more sophisticated than what we're going to cover here, but it doesn't say like, oh, here's my estimated, box office gross for this movie. It's like, oh, if you change this piece of the plot and this character is, a woman instead of a man, and it happens in Amsterdam instead of in Moscow, then it'll be more successful, and darn it actually works. And the people in Hollywood are furious. They hate it. It's like the nerds taking over. Yeah, but hey, I don't mind. Somebody else has a question?
I was just going to say, as a devil's advocate, there's kind of no way on the Netflix app to browse without looking at recommendations. So I would say, of course, all of their watches come from recommendations because there's no other way to find movies.
No, very good, but here's the thing. Why is Netflix so aggressive about pushing its recommender system? Because much more aggressive than, say, Amazon. Right? Amazon also puts a lot of recommendations in front of it, but they put out information as well. Is that the secret to Netflix's business, just as a quick parenthesis before we go on to the actual content of the class, is that they don't want people to rent blockbusters from them. Because you pay a fixed subscription fee. And if everybody just watched the latest Hollywood blockbusters, they would go broke. They lose money. When you go and watch the latest, hit, that costs them more money to acquire than they're going to make from you. So their whole game is to drive demand towards the long tail. As a result of which they need a very good recommender system. Part of why the Netflix recommender system is better than the Amazon is that it's more important for Netflix. Amazon at the end of the day, I mean, I'm painting with a very broad brush here, but Amazon at the end of the day doesn't really care if everybody just buys the same items, right? It actually simplifies our logistics. Netflix, Netflix has this huge collection of obscure British TV shows from the 70s that cost them nothing. The more they make you watch those, the more money they make. Right? But here's the interesting thing is that also because renting something from Netflix costs you nothing. I mean, if you buy something from Amazon, you paid money for it. Netflix, you already have the subscription. So what happens with a lot of people that become Netflix addicts and become enamored of the recommender system is it recommends some crazy thing like, oh, why don't you watch Faulty Towers? Have you guys heard of Faulty Towers? I recommend Faulty Towers. Hey, one of the things you can do for extra credit on your second assignment is enter yourself into your system and see what it recommends to you, right? Like eat your own dog food, right?
That maybe is the reason this is totally.
And we also have, projects where you build a spam filter and apply it to your own email, right? This is, the real applications are there. But to go back to Netflix, right? They make these recommendations. They sound weird to you at first. But you're like, okay, I'll try that out. And then you actually really like them. At which point you go like, wow, this system knows me so well. It's just doing a bunch of data mining, but it is uncanny how well it can wind up knowing you. Now, truth in advertising, what Netflix uses today is not just the algorithm that I'm going to talk about here, right? It's things that came out of the competition, but it's actually still, to the best of my knowledge, an ensemble, we'll talk about ensembles as well, of a bunch of things that actually include these things still. And even then, like, just doing what we're going to talk about here actually gets you most of the way. And then to get a few more percent, you can do much fancier things, but this algorithm that I'm going to describe here actually gives you most of the power of something like the Netflix recommender system.
I was just going to add that you said about Amazon not caring as much as Netflix does. Well, the Amazon Instance Video just announced, I think yesterday, that they are going after Netflix.
Well, so now they do,
so
but
now
for
they're
different,
gonna care
so
about
in that
that.
particular, I mean, Amazon is a huge thing, right?
Yeah.
In that particular market, yes, maybe they do. But again, the interesting thing is that in that market, Amazon's model is even more different because you just buy Prime and then you get the movies for free.
No, that's what they announced.
No, yes, so you're right. You're going to start.
They're starting
yeah,
separating
yeah,
it
I mean,
out,
yeah. Amazon is out to kill Netflix. Yeah.
I don't know. I wouldn't say that, but I'm saying that they're not
I
going to care
would.
more about. They're going to care more about the recommender system.
Hey, at the end of the day, we the consumers are we benefit, right?
Yeah.
And if you work for Netflix and they go broke, then you can go work for Amazon. So.
It's always good.
Yeah, it's always good. Exactly, it's all good. Okay, so here's the recommender problem, right? Is I want to predict whether you will like a web page, newsgroup posting. This is actually where these things began, was things like newsgroup postings. Can I find newsgroup postings that will be interesting for you? If you look at the original paper, this is what they were looking at, which sounds incredibly quaint now. Or movies, or books, or CDs, or just about anything. There's some class of items, and there's a set of people, and I want to figure out what items to recommend to whom, right? And the thing is that, we live in the age of the internet of infinite choice. Anybody can buy anything from anybody anywhere, right? But you can go to Barnes & Noble and browse through the entire, bookshelf of like mystery novels. But on Amazon, they have, a million mystery novels, and you can browse through them. So this becomes very important, right? And now, what people initially did was the obvious machine learning approach, was to look at the properties of the product. Like, for example, you could try to recommend a movie based on the genre. Do you like action movies? Do you like comedy? Do you like, romantic movies, foreign art movies? Or the director, or the actors, and things like that. Okay? And this is not terrible, but it's weak. Because people are complicated, right? Your tastes are not that predictable. You can't just predict, even after I've told you the genre of the movie and the actors in the studio and blah, 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 and the marketing budget, that tells me a little bit about how likely you are to like the movie. But hey, what about the actual plot, right? And how good it is and things like that. But those things are very hard to measure. So the brilliant idea that the people who invented collaborative filtering had was, no, let us not look at the properties of the product. Let us look at what similar people liked. We're going to use other people as a guide to whether you will like the product. And now people are complicated, but they're also very similar, and they influence each other. So this actually turned out to be a phenomenal heuristic. The entire industry of collaborative filtering is based on this idea. And now what makes somebody similar to you, right? That's the whatever, $1 billion question, right? And what we're going to use as a surrogate for that is that you have the same likes and dislikes. You gave 5 stars to the movies that he gave 5 stars to, and 1 star to, right? So you have similar tastes. And now if he gives 5 stars to a movie that you haven't seen, well then, yeah, maybe you'll like it as well, right? This is the basic idea, right? Everything that we're going to see is just an implementation of this idea. And somebody had to have it one day, but once they did, then they started. Then what they did was very, kind of like typical machine learning process. Then they said like, oh, well, this is obviously a nearest neighbor type of problem. Let's apply nearest neighbor. That didn't work so well. And then they tried, bazillions of things, like literally hundreds or thousands, right? And most of them didn't help, right? This is your experience in real life, right? But a few of them made a huge difference. And so what we're going to see here is the basic nearest neighbor algorithm with those few things that made a huge difference. And as I said, at this point people use all kinds of machine learning for this, including much fancier things, but this still works pretty darn well. Okay?
So if I do not want people to figure out what I like or dislike, I could elect not to participate.
Oh yeah, of course.
Right, and so this only works as long as the community is doing.
No, in fact,
likes
there's a
and
very
dislikes.
important problem in recommender systems called the cold start problem. The cold start problem is the system is only useful once people have given a bunch of ratings to it, but they will only start rating, like, why should I rate movies if I get nothing out of that, right? So getting the wheels turning is actually a difficult problem, and it can be a cause of failure. Usually you need some way to induce people to rate the movies or some way to bootstrap it such that people are encouraged to use it. And then once they use it, right, it's the power of big data. The more people you have, the more ratings, the better this gets. Right? It's the network effect of data. You have more data, the product is better, so you get more users, so you get more data. So you make the product better, so, right? This is why it's very hard to catch up with Google and Microsoft when it comes to search, right? Because, yeah. Okay, so how do we do this? We're going to represent each user by a vector of ratings. So U for Netflix, and of course, I'm oversimplifying things a little bit, because people have by now put a lot of work into this, but the first level approximation, U for Netflix are just the vector of the ratings that you've given to various movies, right? You gave, 5 stars to Terminator and 4 stars to Ex Machina and whatever, right? Which means you're a fan of sci-fi, but whatever, okay? And now, the ratings can actually be of 2 types. This is actually an important thing, right? They can actually be implicit ratings. So there's the explicit ratings, which is things like giving stars to a movie. But a lot of the collaborative applications of collaborative film do not involve you having given ratings to anything. What they do is they get implicit ratings from your behavior. Like, for example, if you click on a page, that means that something was interesting in that page for you. If you don't click on that, so it's just a yes, no. So, for example, Microsoft at one point built a system for Microsoft, network, where this was like, well, the things that you clicked on, right, were the things that are interesting to you. The things that you didn't click on are things that are interesting to you, and not can we generalize from that, right? And again, this could just be like, I bought this product, I didn't buy this product, right? I went to the market, I bought these 10 things, I didn't buy those 1,000, so those are my implicit ratings. Those are just Boolean, but often just Boolean ratings, when you have a lot of data, are pretty useful, okay? So at this point, we will ignore which of these 2 sources this came from, whether they're implicit or explicit, in the knowledge that either will work. Okay? Although, of course, there can be variations in how you do things. Okay, so here is the whole algorithm that you have to implement in just 2 formats. Okay, and of course, then you have to make it work fast enough. But it couldn't be that boring. Right? But you get a good feeling of power from implementing something. This is like one of the rewarding things about machine learning is that you implement things that are ridiculously simple and then they do amazing things. Whereas your friend next door is like coding away into the night, right? And you just leverage the data. So you will work into the night doing different things, but like there's no free lunch, or at least there's no free lunch, but there's different prices of lunch, right? And the data science lunch costs less than a software engineering lunch is one way to put it. But anyway, so here's the first formula. I am going to estimate your rating for each item. So R is a rating, R hat is the estimated rating, and I ranges over the users, and K ranges over the items. Okay? So your entire training and test data, as usual, is one big matrix, right? The columns are different movies, let's say, and the rows are different users. Okay? So how do I estimate the rating of the ith user for the kth item? Your rating is going to be your average rating. First, I'm going to show you this first, and then we'll see why these things came about. Right? There's a reason for every part of this, but let's just first see what it is. It's going to be your average rating, right? Your average over all things that you've rated. On average, you get 4 stars or whatever, right? Plus, this is just a normalizing constant, to make sure that once I do the weighting, it's like things are still in calibration of the sum over your neighbors. Okay, and we're going to have to pick some set of neighbors for it. We typically don't use everybody because that would be both very expensive and actually do slightly worse. Okay, the number of neighbors that we use in collaborative filtering, you'll get to play with this, but it's typically higher than people did in traditional nearest neighbor. Instead of 3 or 5, which are the 2 most popular values of k, it might be something like 20 or 30. Okay, so but you have to pick that number, and then it's going to be a weighted average, right? So this is the weight between item I, between user I and user j. So there's going to be a weight for every pair of people. And the intuition behind that weight is it's going to be higher the more similar you are. Okay? So if someone is very similar to you, they're going to have a high weight, and their tastes are going to count for more when predicting yours, right? Makes sense. Okay? So it's going to be the weight of the jth user multiplied by the difference between their rating for that item and their average. Okay? So you know what all these quantities are, right? Modulo the W and the alpha, which I haven't told you how to compute them yet, you could go and implement this right now. Of course,
What is alpha? What is alpha?
What is alpha is just a normalizing constant. Alpha is just going to be the sum of the absolute values of all the weights, right? There's no big suspense there. Okay? The really interesting question here, and that's what the second formula is like, what is that weight? Right? But at this point, and I haven't told you why we do some of the things that we do here, but we'll see that in a little bit. But at this point, you could start implementing this. Okay?
So, on the first term, the average of R
Mhm.
I, did you say this is the average rating of all the users? in the
It's
system?
no. It's your average rating over all movies. So let's say you rated 500 movies.
So I see. So that's why you don't have a K in there.
Yeah, because
K
it
is
only
the
depends on
items, because
us.
you're doing all.
Yeah, exactly. Yeah. Okay, so now, how do I measure the similarity of 2 users? And again, the folks, this was at the University of Minnesota. They had this project called Movie Lens, and then they actually started, as we computer scientists do. Once they realized that they had this, amazing thing on their hands, they did this startup called Net Perceptions. And in fact, the first recommended system that Amazon had was built by Net Perceptions. And then they wanted to scale up more, and the stuff didn't scale, and they started doing other things. And in some ways, we're actually worse. But for Amazon, scale is very important. Okay. So what they found that worked really well was not Euclidean distance or Hamming distance or any of the things that we've talked about before. It was actually something that is a very, trivial thing in statistics, but they tried it among other things. And that is what is called the Pearson correlation coefficient. How many people here have heard of the Pearson coefficient before? Several of you, right? Maybe 15 or 20%. But hey, right? It's not a big new thing. But what is the idea? Well, you have two vectors, right? And the correlation coefficient is just measuring how similar those vectors are, right? But how are we going to measure that? It's in the following way. The numerator is just a correlation between the 2 users. Meaning what? It's the sum over all the items of the product of the difference between the first user's rating and his average and the second user's rating and their average. Right? Again, if you know your stats 101, this won't surprise you, right? I'm interested, two things might have different averages, right? And be highly correlated if when one is above the average, so is the other. And when the other one is far above the average, so is the other, and the same thing will be below. Right? So 2 things don't have to have the same average in order to be correlated. In fact, they might have the same average and be uncorrelated. Right? So I need to subtract the average first because I'm just interested in whether things vary in the same direction. I'm not interested in what the average is. Okay? So
Sorry, what's J again?
J is ranging over all the other users.
All the other, okay.
Right? So oops, yeah. So Wij, right, is for, there's going to be a matrix of this, right, for every, where the ith entry is for the pair of users I and j, okay? So the similarity between users I and j is the correlation coefficient between them, right? And now this is going to range, okay, over the items, okay?
Does it have to be the common item that both users have rated for?
Exactly. This is one of those details. Is that like in general? Is this what you're going to ask? Yeah. This is actually on the next slide. Right. It's one of those details. In general, you will not all have rated all movies. Well, heck no. Even the biggest Netflix addicts don't come close to that. So the way this is typically done is like we look at only the subset of items that both users have rated. But for the moment, let's just assume that it is of all items. Just rigorously it would be, except that we don't have the data.
So how those companies like Amazon and Netflix, how do they, on the weights of a pair, how do they account for things like, proximity in gender,
They don't in this version. There
I'm
are
sorry.
versions that take things like that into account.
I was just gonna say gender, like age group or
They don't.
whatever. They don't.
They don't. And the reason that's not a done thing to do is that if people of your gender and age group have similar tastes to you, this will come out without explicitly considering it.
Yeah.
And if they don't, then never mind. This is the power of data, right? It's like you can actually do things at a much finer level than these coarse categories like age and gender. It's like the people are similar to you, whether or not they're the same age and gender.
Yeah.
Yeah. Okay?
So this is the passé type, like the old style of learning.
Yeah, yeah. Which is not to say that then you can't add refinements on top of this that bring back some of those things. We're just trying to look at the basic idea here.
But then this has a flaw, right? Like, let's say someone likes movie A, B, C, and he has rated 555 or 454,
Mm-hmm.
and the other guy, he has totally opposite taste, and he rated 121. So average would be. Average
Hold
would
that
be the
thought.
same,
Hold
right?
that thought. This is an important issue, but it's actually solved in what I've already shown you. So hold that thought. We'll get to that in just a second.
One question.
But you're right. That's actually one of the crucial issues that they found. Yeah.
So you said the weight would be higher if people are similar, right?
Mm-hmm.
So I am completely similar to myself,
Mm-hmm.
but the value for this would come out to be 0 in that case.
No, it wouldn't. No, because remember that this would be making I and J the same, right?
Yes.
In which case, think of, to simplify, let's suppose it's either, your rating is either 1, 0, or -1. Okay? When you give yourself 1, when you give 1, you also give 1. So
Right.
things go up and down exactly in tandem. So the correlation coefficient between you and yourself is 1. If you don't believe me, do the math at home and come back. It'd be fun if you completely revolutionize statistics, but it's unlikely to happen. Now, so this is just the covariance between them, but the problem that this has is that it ranges arbitrarily, right? And in particular, if all we had was the numerator, people whose ratings are more variable, right? People who are more excitable and give either 5 or 1 would look more correlated than people who give only 4 and 2, and that doesn't make any sense. Okay? So we have to normalize. So we divide by the product or the variances of the two individuals. Okay? So one way to look at this is like this. Okay? Is to break this up into these two pieces. Okay? This is not quite correct because the summation sign is on the other side, but you get the idea, right? You want this thing to be normalized. Okay? This normalization constant, right, is a very natural one, right? It just notice if this guy, right, is varying a lot. Oops. If this guy is varying a lot in the numerator, it's the same thing in the denominator. It's also going to be varying a lot in the denominator. Okay. So the only purpose of this is to make this range between -1 and 1. Okay. So if two users are completely correlated, in particular you and yourself, right, you will have a Pearson correlation coefficient of 1, right? Two people who have completely randomly different tastes will have a correlation coefficient of 0. You and your anti-you, right, the person who is exactly opposite of you in every taste have a correlation of -1. And by the way, if someone does have tastes that are exactly opposite of yours, that's great. I can predict what you will like. Right? Every time they give a 1, you're going to give a 5. And people actually tried this, but it didn't work so well because that tends to not appear to be very lazy. But
So people have different scaling perceptions, right? So
Mhm.
people never give 10 out of 10.
Yeah.
So don't we then scale? maybe
No, but this is actually, that's part of what this is doing, right?
this
Is
is
it like,
scaling out the average?
yeah. You know, suppose to people, let's take you and him, right? Let's suppose that you and him have exactly the same tastes, right? But you are more, enthusiastic. You're more extreme in your tastes. So let's say every time you give a 5, he gives a 4, and every time you give a 1, he gives a 2, right? You have different scales, but actually his tastes are highly predictive of yours. Okay? So what I want to actually do, I want to make this measurement independent of whether you are more excitable or less, right? If you're one of those people who just are like, yeah, not bad, right? When they love the movie, right? Or, right? Then the information is still there, but I need to recalibrate. Okay? So this is the recipe. You can go and implement it tomorrow. Or even tonight, if you feel like it.
So, back to his question, what is that fundamental problem that, what was the actual problem that?
If you have no overlap in rating, is that what you're referring to? The
No,
idea
if
that-
two users have no overlap in rating at all, then they will not. Then you just ignore them.
Right.
I mean, you can't compute this at all. But in particular, you have no. Like if you and him have no overlap, I have no basis to predict your movies from the ones that he's watched.
You just want me out of that set. I wouldn't be in the nearest.
Having said that, some of the newer fancy methods actually allow you to generalize beyond that. Like there's these methods based on dimensionality reduction, on doing matrix decompositions, right? If you're not familiar with this, never mind. But those methods can actually find similarities between people, even if they don't have movies or even common. But anyway, yeah.
So for the online dating business, they must have something similar, right? What are the K in this case?
Oh, it's like your Twitter, right? And it's the things that you liked and the things that I liked.
So would K
Or the
be
things that you
hiking
retweeted and I
or
retweeted, or the things that whatever.
common interests? So
Yeah.
your K, instead of being items or movies, you just.
So actually, in the online dating example, think
Oh,
of
you're talking about online dating?
That's what I was
Yes.
talking. I was
Oh,
saying.
no, online dating is, I thought
What
you
did I say? Sorry, did I say
No,
something?
I thought you said online data.
Oh no, online dating.
Oh,
the-
no,
those
online
sites.
dating, they still do it based on your properties.
So K is your properties. in
No,
this case,
no. For online dating, they do not use collaborative filtering.
They do not.
But there's the change in that, right? The
They're
Tinders of the world, swiping left and
No,
right.
yes.
Swiping left and right is this. It's collaborative filtering, where you're rating a profile by looking at it,
And you're going like.
and you swipe left or right.
So yeah, by the way, right, if I was you, I'd go to Tinder and offer to do this for you.
I've tried.
And?
So I have Scruff, I don't have Tinder, Grindr's and R-Shop, or Python, so it's a longer story.
But I thought of that, right? Like it's a very intriguing idea because for Tinder, that data is available. Every swipe is exactly this yes/no
Yeah, so
in its purest form.
So that's what Scruff is doing.
Yeah.
They have the same swipe left, swipe
Yeah.
right. That's a rating, and then that's computed into it's items of
Yeah, there you
It's
go.
the whole thing.
The classic data systems do it based on your profile.
Yeah.
Now, what somebody has done, right, as another option, which I think is harder but is even more intriguing, is like they actually try to do image understanding on the pictures and figure out what makes somebody attractive to you. Now, that is a really interesting machine learning problem. But I probably won't go to Twitter with that yet because it's too hard.
They do collaborative filtering for that?
No, as far as I know, Twitter isn't doing this
No,
yet.
I mean the image understanding and that.
No, Twitter doesn't do that, but somebody actually scraped some Twitter data, don't ask me how, right? And did this. They published it in, KD Nuggets. And, and their results were not that exciting, right? I mean, even just detecting the face properly is hard, let alone subtle things like what makes somebody attractive or not. But in principle, right?
It's a whole lot easier to get people to swipe left or right.
No, yeah, I mean, it's like,
much
it's a,
easier to get them
like
to rate it
the
for you.
beauty of it is that, like, for a machine learning, project, like, this is like your quintessential supervised data, right? So they've got the goods, and they're either already doing this or going to start soon, right? Because then they can match you up with even more potential people, right? So that's what it's all
I have a
about.
question.
Mm-hmm.
So in the first equation, the recommendation rating seems to be heavily dependent on my average rating. So is
Okay,
that...
so let's get to that, okay? So this was the basic formula, but now let's look at some of the issues, right? This is what the guys tried initially. the net perceptions people. They did the obvious thing, which was to just say your average rating, right? Never mind. Your predicted rating for item K is just the average of the predicted ratings of your neighbors, right? Weighted by the similarity, right? Isn't this the obvious first thing to try? This is the first thing that they tried. And this was okay, but not great. Why did they go, and by the way, the alpha, as I already mentioned, is just the sum of the absolute values of the weight, so that this thing is properly normalized, okay, nothing dramatic there, right? Also, like as I already mentioned, the n in the neighbors could be the whole database or only a subset, which you could pick by cross-validation. But now, why did they do this instead?
Because
Oh,
it's,
because
so
to fill in the.
it makes it relative to my
Yes. It's a slightly different problem from the one we were just talking about, is that suppose you have two people that have exactly the same tastes, but one of them is a very happy person, and the other one is a big grump. Right? So whenever the happy person gives 5, the grump gives 3. They like the movie the same, but one of them is just grumpier, right? I mean, like people are like, this is real, right? So you give 5, they give 3. You give 3, they give 1. You give 4, they give 2, right? So you are moving completely in tandem. But yet, by this measure, right,
You're moving the same way.
you look very different. So what you need to do, you need to subtract your average. So that when the grump is above his average, and the happy person is above their average, right, then, now what happens, like when the grump gives 3, that predicts that you give 5. And vice versa, right? So there's good predictability there, but you do need, to subtract. Notice that what this is doing, right? Another way to write this equation is as follows, right? Is that Rik minus Ri bar is equal to blah blah, right? So what I've done there was just to replace the ratings on both sides by the difference between the rating and the average rating. So people may have different averages, right? The happy person has a high average, the grump, has a low average, but they can still be very highly correlated, and that's what we care about. This was one of the few. So the things that they found that really made a difference, like one of them was using Pearson, right? They used a lot of stuff, including Euclidean distance and whatnot. Pearson was a hit. Another thing that was a huge hit was this thing of subtracting the mean, because people do vary in how grumpy or happy they are. Yeah.
But I think most of the time it's not about your graph. It's the scaling. Like there are people who don't give extreme ratings, right? So I would rather scale it.
No, but these are both real. The scaling issue is taken care of by Pearson, which is part of why Pearson was good, right? This takes care of this. Again, it's like one person being more extreme, more excitable, right? Someone on average might give 3, but they go to 5 or 1, right? So that's taken care of by this. Yeah. This part, right, takes care of the fact that someone's just consistently grumpier, or like you could be grumpy and have low variation, or you could be grumpy with high variation. So all those combinations can happen, but this combination of Pearson and subtracting the average actually takes care of both. Okay? Mm-hmm.
Has anyone tried to use average based on a feature? Like, for example, average based on genre.
No, as I said, this was the first thing that people tried, but that didn't work very well. The revolution really happened when they started doing this based on people's similarities rather than features of the product.
So what sort of behaviors can, like the grumpy person, this is account for? So for example, is the contrarian behavior kind of a
No, yes, I mean, as I said, people
accounted for here, or?
This is a natural thought, right? If someone is a contrarian, they're actually a good predictor, right? But that actually turns out to not be such, because there aren't that many contrarians. There are people do vary in how grumpy they are. People do vary in how spread out they are. Another pattern that has been consistently found is that people tend to only rate movies when they really love them or they really hated them. So the ratings, are actually not a normal distribution. They tend to be skewed. If you kind of just like the movie, then you might not bother to rate, or at least many people won't, right? There are people who religiously rate every movie on Netflix. But what often happens, like when you really love the movie, you want to rate it, just to share the love. And when you really hated the movie, you want to tell everyone that movie sucks. You want to punish them.
If someone watched the movie to the end, they probably liked it.
Well, no, yeah, but now that we have streaming, right, then maybe you can use that as a feature, maybe they do. By the way, when things moved to streaming, they had to change some things about how the recommendation system is built, because it is a different system with different constraints. When it was, when they started doing this, they just sent you the the DVDs by mail, in which case they didn't know what they watched until the end. But yeah, I mean, one area where this is used a lot is in commercials, right? When you go on YouTube, right, the fact that you're allowed to cut out of the ad, right, is actually serving everybody, because it tells them whether you are interested in that ad or not, which is better than them not annoying you by showing an ad you don't want to see, but it also helps them to next time, do more of the ads that you watch until the end.
I never keep them, this is skips.
I read somewhere that they also, the K movies, they also victorize that with the movie properties.
Can you what? The K?
The movie they victorized.
No, so yeah, so these days what people use is they use hybrid systems, right? They actually go back and, because things like the genre and the actors, they do have some information, so why throw it all away, right? So they use that, they use other things. Like, for example, one of the things that came out during the Netflix prize was that there are a lot of temporal effects. So the rating, if you watch two movies one after the other, the rating of the second one is affected by the first one. If the first one sucked, the second one looks good even if it's just okay. And again, this makes sense, but somebody had to, actually discover it and put it in the system, and there's other things like that. And maybe there's more, right? I mean, like, this area is very, obviously very intensely explored by now, but I think there's still room that, like, if you come up with a new, better way to build collaborative filtering systems, you can do a startup and go to town with it, because everybody will want it, right? It goes directly to their bottom line, right? One of the nice things about machine learning is that the benefits are often highly quantifiable. It's like, you were using that, you're using this, you do the A/B test, and this makes you $1 billion more a year. And they only paid you, 10 million, which made you rich, but to them it's still a huge win, right? So there you go. Okay. Questions about collaborative filtering? Oh, sorry, let me make sure I went through all of these things. Yeah, we basically touched on all these. Yeah. So now you're ready to do yours, or to start at least on your, part of the second assignment will be stuff that we'll cover next week about, Bayesian and whatnot. But you're ready to start doing the implement. So, in case you haven't looked at it online already, right? The first part of your assignment is implement the collaborative filter using this algorithm and apply it to Netflix.
So on the prediction side of this, I'd have to predict a rating for all items in order to find the set to recommend, right?
Yeah, in principle. Right? Again, now there's a lot of scaling issues, right? And again, you will run into some of the scaling issues in your project, but imagine being Netflix or being Amazon. So they're gonna, in principle, you will want to range over every possible item. In practice, you may want to find, ways to pre-filter a lot of those things.
Okay.
And again, if there's time, we will talk about how to do some of those things more in general. For instance, based learning in general. Other questions? As you can already tell, you're going to have a lot of fun doing this project, right? And it'll be so good for your self-knowledge. One of the things that a lot of these projects often discover is that people, dating site is actually a great example, right? The guys who do OkCupid, right? They do a lot of them. The guy even wrote a book, right, called Dataclysm. I don't know if you've seen that. It's about how, people say, oh, I like this kind of person today, and then you look at the people that they actually chose today, and it's a big difference. So, yeah, human behaviors. Okay, any questions about collaborative filter? Okay, very good. Let's see how we're doing on time. Okay, we were never going to go over everything that's in the slides, and I encourage you to look at some of that at home and the book and whatnot. But we will go over some of the things here and a few more next week. Okay. So, but in the meantime, let's use the remaining 10 minutes that we have as well as possible. So, let me just go. Yeah. So here's the next most important thing to know about. It's the curse of dimensionality. And in 10 minutes, I'll be able to tell you what the curse of dimensionality is, but not how to solve it, as well as which you're going to have a lot of nightmares between now and next week. Okay? Or you're going to read ahead in the book, which you could, or in the slides. But so what is the curse of dimensionality? As I said, the curse of dimensionality is a really important problem in machine learning. And there's actually a term that was originally coined by a famous control theorist, Richard Bellman, the guy who invented dynamic programming. He had all these problems for which, as long as you were in low dimensions, like 2 or 3, everything went beautifully, and once you got to high dimensions, everything fell apart. So he called that the curse of dimensionality. In his case, he was just thinking about efficiency issues, but in machine learning, it goes way beyond efficiency. The whole learning problem is you go, and in machine learning, it's not like graphics. Like we're not in 3D. We are in 1000D or 10,000D. Okay? So the curse of dimensionality really, really hits you. So let's look at what it is, right? Imagine that your instances are described by 20 attributes, but only 2 are relevant to your target function, right? Then your nearest neighbor algorithm is going to be crap. In fact, Bryman, Friedman, Ocean, and Stone, kind of like developed decision trees in parallel with Quinlan, but more on the statistical side. One of their early papers had this comparison with decision trees and nearest neighbor, because back then nearest neighbor was the standard for what is called nonparametric learning, and did the following very devious thing, right? They started out with a function of whatever, let's say 2 attributes, and nearest neighbor and decision trees were both great. And then they started adding the relevant attributes. And the decision tree was just marching along totally fine, and the nearest neighbor was going like zzz. Right? By the time you got to 20, or I forget the exact number, nearest neighbor was as good as random guessing. Right? And you can see why. Because like the signal in those 2 relevant attributes, even if those 2 relevant attributes completely determine the class, right? Let's suppose that the class was the XOR of those 2 attributes, right? There's a perfect decision tree or a perfect symbols for this problem, but nearest neighbor doesn't know. The random noise in the other 18 makes whatever examples look like whatever others, and it's random guessing, right?
It's the feature selection.
No, so this is one of the first things that we're going to look at is doing feature selection for nearest neighbor. And indeed, if you're ever going to do instance-based learning, one of the first things that you have to have in your toolkit is feature selection, precisely because of this problem. But as we'll see, even feature selection will not, it will help, but it won't completely solve the problem, by any means. Yeah.
Feature selection means that you remove some features, so it means that you add weight to some.
Yeah. Well, you can also do feature weighting. That's another option, more sophisticated than feature selection. But the easiest thing to do here would be like, if I can somehow figure out which are the 2 relevant attributes, I'll get rid of the others, and then only measure happiness on some of the ones that matter, and then nearest neighbor is back to being great. Okay? So that is one thing that you can do, and again, it helps, but it doesn't completely solve the problem. Okay? But here's the thing, right? This is the part that's actually hard to get your head around. Let's suppose that all 20 features were relevant. And I think, now nearest neighbor is back in great shape. Actually, no. Nearest neighbor has trouble with a lot of features even when they're all relevant. Which makes big data a double-edged sword. And by the way, again, this is particularly bad for nearest neighbor, but it applies to everybody. As you get more data, as a rule of thumb, right, more data means a bigger table. Okay? More lines in the table means more instances. That's all for the better, provided you have the computing power to deal with them, right? It's more information. More columns means more attributes. Now it's a double-edged sword. Potentially, those are good attributes, so you can do better. But just the fact that you have more attributes has suddenly made the problem a lot harder. Right? And what we're going to see, maybe today, maybe next week, is why. Okay? When your instances are high-dimensional, nearest neighbor goes astray very easily. Point 1. Point 2. Things that were easy, this is how like Bellman's original idea is that problems that were very easy in low dimensions, suddenly in high dimensions they become extremely hard. Okay? And third, and maybe worst of all, everything that you know about the world, that you've learned from a beautiful visual system, in 2D and 3D, does not apply in high dimensions. Even the notion of the very notion of similarity, which is what all instance-based learning is based on, it breaks down in high dimensions. The world of high dimensions is like something out of the Twilight Zone. Everything is very, very weird. And in fact, Usama Fayyad, the famous, data scientist, famously said that if human beings could see in high dimensions, we wouldn't need machines. Right? In 2 dimensions, you can see like, the border is no trouble. The problem is that in high dimensions, you can't see what's going on. And what's going on is extremely intuitive. Let's look at a few interesting examples of that. Prepare to be disturbed. The normal distribution, right? You can have a 1D normal, right? 1D Gaussian, 2D, 3D, etc. Right? Now, what is the essence of a normal distribution? Is that the data is all concentrated around one point, right? Essentially, the data comes from one point, and then there's a little bit of fuzz around it. Okay? Now, guess what? In high dimensions, most of the data in a normal distribution is not concentrated near the mean. If you draw a ring, right, of some thickness, as you go out, there's a point at which there is more data than there is near. In other way to put this is like the bell curve in high dimensions looks more like a donut than like a bell. Strange, huh? But the reason is that the amount of, the density has gone down, right? It goes down, exponentially, in fact, quadratically exponentially, right? But the problem is that in high dimension, in 1D, the bands are like this, right? In 2D, now you actually have a whole circle, right? In 3D, now you actually have a whole shell, right? You have more and more volume. Okay, so now there's this competition between the density is going down, but the volume in that shell is going up. And the volume wins at some point. Okay? So this whole idea that normal distribution is something localized at some point with some fuzz around breaks down in high dimensions. Okay, so this is the first weird thing. Here's another weird thing. Think of a cube and sprinkling down points uniformly at random in the cube. Okay? Most of them will be closer to another point than to a face of the cube, right? The great majority of them, right? Guess what? In high dimensions, if there's a sufficiently high dimension at which most points are closer to a face of the cube than they are to the nearest point. And the unfortunate thing about this from our point of view is that being near the face of the cube means that you're in no man's land. Nobody knows what's happening on the other side. You know how the old maps used to have there be dragons, when they didn't know what the map of the world was there, right? There'd be, the ocean, and then here be dragons, right? Well, when you're near the face of the hypercube, that's where the dragons are, right? Who knows what's going on there, okay? Unfortunately, it's the same problem again as you go to higher dimensions, right? The same amount of data means the cube is populated more and more sparsely, right? Increasing the number of dimensions exponentially increases the number of data points that you need to have in order to have the same data density. Mm-hmm. And data density is what drives machine learning. If you don't have points near you, like if your nearest neighbor is way far away, then you're hosed because it doesn't say anything about you. It's too different. Okay? Here's another one. Let's say I have a straight line, and all your points are at equal intervals on the straight line. Okay? There's a data point at 1, 2, 3, 4, etc. 0 there. Okay? So let's say that this is your test point. Okay? You have you have a tie for nearest neighbor, right? Between this guy here and this guy here. You agree? So two guys tie for nearest neighbor. If you're in 2 dimensions and you have a grid, how many points tie for nearest neighbor? Right? Now there's a grid here. Maybe I should have done this on a separate page. There's another, right? The up, down, left, and right are all at the same distance from you, right? And so the moral of the story is that, like, if you're in the dimensions, there are 2D points that are at the same distance from you, right? Meaning that if you're in 1,000 dimensions, there's a tie among 2,000 points for your nearest neighbor, right? As a result of at which point maybe you're probably better just guessing the most frequent class. Okay, this is another unfortunate thing that happens. But here's another one. And this actually illustrates why the crystal dimensionality isn't just bad for nearest neighbor. Decision trees approximate regions by hypercubes, right, or hyperrectangles, right? Let's suppose that you're in a situation where your positive class was a hypersphere, okay? Right? Inside the hypersphere, everything is positive. Outside the hypersphere, everything is negative, okay? And let's say that let's think of the sphere to start with. You have a sphere, the points inside the sphere in 3D are positive and the ones outside are negative, okay? Now let's say that I'm going to approximate the sphere with a cube, right? That sits outside this, so the sphere is inside the cube, and it touches the cube, at the center of the faces, right? You see what I'm suggesting? This is not a bad approximation, right? In 3D, right? You'll get everything inside the sphere correct. You'll get everything outside the cube correct. The corners of the cube you will get wrong, because your approximation says positive and rather than negative, okay? Now you see where this is going, right? If what you have is, a hypersphere and a hypercube in very high dimensions, you will get practically everything wrong. Because most of the volume of the cube is in the corners. In fact, as the dimensionality goes up, the fraction of the volume of the cube that is contained in the sphere goes to 0. It's mind-boggling, but it's true.
Is there a way to visualize that?
Well, I wish there was, but there ain't, right? If you invent one, please come talk to me. And I will kill you right after you tell me. And now here's the last one. Volume of a sphere, right? Suppose that I give you an orange, right? Some fraction of the orange is actually the skin, okay? And you want to throw away the skin and eat the pulp, right? The pulp is the tasty part. You don't want to eat the skin of the orange, right? Now let's suppose that the skin of the orange is the last, make up a number. Like I'm going to call it 10% just to make it simple. Okay, maybe it's 5%. Like, let's say, if you look at the radius of the orange, right, like the first 90% are pulp, tasty juice, and the last 10% are skin. You don't want to eat them, okay? But you peel the orange and you eat the pulp, right? You know what happens in high dimensions? At this point, you can probably guess what's going to happen in high dimensions. The orange is all skin. There's no pulp. You peel it, you peel it, you peel it. There's some infinitesimal thing down there that's a tiny drop of juice. But most of the orange, there's nothing to eat there. It's all skin and no pulp. And this is an easy exercise to do, right? Look at the formula, right, for the volume of a hypersphere, right? And this depends on the power of the radius, right? And guess what? As the power is the dimension, so as the dimension goes up, the difference between 0.9 of the radius, right? This basically is like 0.9 of the radius being raised to d, and d is getting higher and higher. So less and less of the hypersphere is within that 0.9 radius. Okay? So things in high dimensions are very, very weird. If they weren't so weird, we would probably already have solved machine learning. But this is like, we're very confused. Even the world's best researchers are very confused by what goes on in high dimensions. Okay? Having said that, we do have all sorts of things that we can do to try to mitigate these problems, and we'll look at some of them next time. Okay? All right?
Yeah, let's just compile it.